Hello, Assalamu alaikum. Hope you are all fine. Welcome to the lecture of Analysis of Subharmonics in Power System. Contents of this presentation includes 12 different portions. Firstly, we will define about the harmonics. Then we will talk about the subharmonics. Then we will talk about how subharmonics affect the power system, sources of subharmonics, why we have to worry for subharmonics in any power system, subharmonics phenomena, subharmonics versus frequency, the effect of net resistance on subharmonics, subharmonics detection principle, protection against subharmonics, conclusion, and the references. So, what is harmonics? Harmonics are generated when the equipment draws current which is non-sinusoidal or the nonlinear to the applied voltage. The electronic devices are non-linear devices which draw non-linear current when sinusoidal voltage is applied to it. For example, we will apply the sinusoidal voltage, then the voltage we will achieve on the output is not sinusoidal, or the current which will drawn from the circuit is also non-sinusoidal. The transformer at the time of charging also draws non-sinusoidal current. This nonlinearity in the current causes harmonics in the system. The sinusoidal components whose frequency is equal to the fundamental frequency is called the fundamental component, and the integral multiple of the fundamental frequency is called harmonics. Now moving towards the basic theme of this presentation, which is subharmonics. The frequency is below the fundamental frequency in a ratio of 1 divided by nth of the fundamental frequency, where n is a positive integer number. For example, if the fundamental frequency is 50 Hz, subharmonic frequency is equals to 1 divided by n into f. F means fundamental frequency. So if we will consider n equals to 2, means the positive integer number equals to 2. So the subharmonic frequency will become 1 divided by 2 into 50, which is equals to 25 Hz. If we will consider the n integer number equals to 3, the fundamental frequency will become equals to 16.66 Hz. If we will take the integer number equals to 4, then the subharmonic frequency will become 12.5 Hz. The subfrequency of 25 Hz, 16.66 Hz, 12.5 Hz are subharmonics. How subharmonics affect the power system? The major problems offered by subharmonics are induction generator effects, torsional interactions, torque amplification, subsynchronous resonance, and transformer saturation. Subharmonics generated from capacitors may introduce errors in phasor estimations. This may cause mal-operation of distance relays. High amount of subharmonics can also affect directionality of the relay. The most of the loads are inductive in nature. The impedance of inductive load depends on the frequency. The subharmonic frequency offers low reactance. XL equals to 2 pi FL. As a result, subharmonic current will be much higher. This makes the subharmonics more severe. In other words, the lower the order of the harmonics, the more severe it can become, as the reactance offered also gets lower, as we can see in the picture. So now we will talk about the source of subharmonics: transformers under no load and light loads, saturated reactors, thyristor controlled motor drives, arc furnaces, arc welders, fluorescent tube lights, energy conservation devices like soft starters, electronics blast and fan regulators, rectifiers, UPS, static war compensators, high voltage direct current transmission systems, and solar power conservation can be the sources of subharmonics in any power system. Why to worry for subharmonics? Voltage distortion is generally very harmful because it can increase the effective peak value and also the RMS current in some devices connected to the network. For capacitor, impedance decreases drastically as it is inversely proportional to the frequency. Under normal circumstances, the voltage distortion in primary electrical distribution network is minimum and can usually be ignored from a practical point of view. Distortion of current wave shape is common particularly when electronic equipment is connected to the network or when non-linear nodes are connected. Current distortion causes overheating due to increase in the losses and affects all the electrical machines like transformer, etc. This causes derating of the equipment. The amount of derating will depend upon the subharmonics which are present in the network and the magnitude of the individual current and resistance. Subharmonics phenomena. The nonlinear loads will produce harmonics by drawing current that are not necessarily sinusoidal. In effect, inductive loads will produce harmonics that are multiples of the fundamental. In a similar manner, when a circuit involving a resistor, capacitor and inductor is connected in series, voltage and currents with frequencies below the fundamental will be created. These are called subharmonic frequencies. When a series capacitor is used to cancel a portion of the system reactance, the system will always end up with the natural frequency, which is less than the system frequency and is referred to as the subharmonic. This subharmonic frequency is defined as like in the formula. So in the formula, FER is basically the subharmonic frequency, FO represents the fundamental frequency, XC, X, XE, XT represents the capacitor generator system and transformer impedance. The generator armature subharmonic currents produce magnetic fields with frequency FER which are induced in the generator rotor. As a result, the induced currents in the rotor produces a rotor frequency defined as FR equals to FO minus FER. In this, FR basically represents the rotor frequency. In consequence, this new added rotor frequency will result in subharmonics subsynchronous, basically armature voltages, which may enhance the subsynchronous currents and may cause generator self-excitation. Subharmonics versus frequency. The highest of the subharmonic frequencies is found at 12 Hz. However, due to the three-phase faults, the subharmonic contribution is seen in all the three phases. The effect of net resistance on subharmonics. The induction generator effect occurs when the resistance is greater than the resistance of the system, producing a negative net resistance. As a result, the negative resistance has a negative damping effect which produces crowing oscillations. Subharmonics detection principle. The theory behind the subharmonic detection is to compare the magnitude of each of the subharmonic currents and voltages that are observed between the user-defined minimum and maximum frequency range with the settings specified by the user magnitude. The nominal subharmonic detector compares the level by estimating the ratio of subharmonic magnitude to the nominal CT by PT ratio. The fundamental subharmonic detector logic compares subharmonic magnitude with respect to the fundamental voltage or current quantities. The subharmonic detector is basically listed in this slide. Protection against subharmonics. Protection relays. A subharmonic protection relay protects against subharmonic oscillations by measuring the voltages and current magnitudes of the subharmonics with frequencies in the range of 5 to 45 Hz for 50 Hz systems or 5 to 55 Hz for 60 Hz system. The relay is composed of 4 sets of currents and 2 sets of 3-phase voltage inputs. Each input can be set to detect individual frequencies from 5 to 45 Hz for 50 Hz system or 5 to 55 Hz for 60 Hz system with 2 levels of detection. So what is subharmonic current nominal ratio? Nominal ratio can be defined as the ratio between the highest subharmonic current in the system to the nominal current, which will be occur between the 1 ampere to 5 ampere. So nominal ratio will be around 8%. So if I will talk about the subharmonic voltage nominal ratio, so it can be defined as the ratio between the highest subharmonic voltage divided by the nominal voltage level 69 volt. So settings will be occur like greater than 2%. So here in this case we have the nominal ratio around 3%, which is greater than 2. Active filters. The active filter works on a similar principle to reactive power compensation, but rather than compensating reactive power, unwanted subharmonic current is compensated. There are two methods of active filtering through a series connection and active filtering through a shunt connection. Figures show a circuit with a non-linear load and a series connected active filter. So here I have two circuits. First one basically describes a series connected active filter with an AC source and a non-linear load. While in the second picture, a shunt connected active filter with an AC source and a non-linear load. Finally, the conclusion is here. Subharmonic are interharmonics with frequencies lower than fundamental frequency. Subharmonics current are generated by many modern loads, cycloconverters, arc furnaces, integral cycle control, etc. Subharmonic effects on important power system components like lighting system in terms of light flicker, transformers in terms of hysteresis, loop asymmetrization and core saturation, protection relays protect power system against subharmonic oscillations by measuring the voltages and currents magnitudes of subharmonics with frequencies in the range of 5 to 45 Hz for 50 Hz system or 5 to 55 Hz for 60 Hz systems. Here we have references. This is all from my side. You are welcome to ask any question related to this topic. Thank you very much for listening to me. Good luck. Allah Hafiz.